Hi. I think a lot of you may have heard his talk on population last spring, and I hope you'll be happy to welcome him back again. Steve Warren is an emeritus professor from the Department of Atmospheric Sciences at the University of Washington, and he has a bachelor's degree from Cornell in chemistry and a PhD in physical chemistry from Harvard. He became a climatologist in 1978 and has been many times to Antarctica, which he's going to tell us about. Steve.
First, I want to thank Kay for inviting me. I first met Kay in 1962. This was a summer program for high school students and teachers at Colorado College. And of all the students who were there, Kay is the one that I've maintained contact with over the years, including visiting the farm in Oklahoma 3 times where Kay grew up. Okay, so my talk today is about Antarctica, and I'm going to talk about both the Antarctic continent and the Antarctic Ocean. First, let's see about this. And you can hear me with this microphone? Yes? Okay. So we'll start out with the overview. The Antarctica is the bright spot at the bottom of the picture, taken by astronauts on their way back from the moon, and you can tell what month this was. The fact that Antarctica is sunlit means it was December. Antarctica is surrounded by a cold ocean that at this time of year also contains a lot of ice cover. The ocean water freezes and it's covered with snow. It's hard to see though because it's also hidden by clouds. In fact, the Southern Ocean around Antarctica is the cloudiest region on Earth. You get an idea of the Earth's energy budget from this picture. If the Earth were a perfect solar collector, this picture would be black. Everything we're seeing there is reflected sunlight. And so what's responsible for the reflection of sunlight is mostly clouds and then secondarily snow and then bright desert surfaces like the Sahara and the Kalahari. Antarctica is an outlier among the continents. This was long ago, a plot of the average height of the continent as a function of the area, and the continents with more area tend to be higher. They all fit on a line except Antarctica is the outlier, and if you look at the distance from the point to the line, you can get an estimate of how much ice is on Antarctica. Well, Antarctica is covered with ice, and the ice is covered with snow. It is our modern example of a continental ice sheet. And in fact, it's about the same size as the former North American ice sheet that covered Canada 20,000 years ago, both in area and in volume. So this picture represents actually about 98% of Antarctica, so it's worth looking at for a long time. And the other 2% is in regions near the mountains where the strong winds blow the snow away and also sublimate some of the ice, so you have bare ice instead of snow cover. Here's the map of Antarctica in the standard orientation with the South Pole at the center and the Greenwich Meridian at the top. It's divided into 2 parts by the Transantarctic Mountains, and the larger part is mostly in the eastern longitude, so it's called East Antarctica, and then the West Antarctica is the other part. Most of the ice is in East Antarctica, about 88%, and in fact, if you removed all the ice from Antarctica, it's only East Antarctica that would remain as a continent, somewhat larger than Australia. And West Antarctica would just be a chain of islands, and that's because the West Antarctic ice sheet is grounded on the ocean floor. For example, at Byrd Station, the surface elevation is 1,500 meters, but the ice thickness is 3,000 meters. So if you remove the ice, even allowing the bedrock to rebound, it would still be well below sea level. These are contours of elevation above 2,500 meters. The highest elevation on the ice sheet is about 4,000 meters. Let's see, then there's also, there's this peninsula that sticks up towards South America. Oh, have any of you been to Antarctica? One? Okay, well, if you were on a tourist ship to Antarctica, probably the region you went to was the peninsula region. Yeah, because that's the most interesting. It's also the easiest access from South America. Most interesting because of glaciers, mountains, penguins, seals. But for a climatologist, we don't go, I've never been to the peninsula. Where I go as a climatologist are the areas where you can make a measurement that will represent large areas. So going to the plateau, to South Pole, Bostock, Dome Sea, there it's that uniform snow surface, whereas near the coast or on the peninsula, you go 2 miles away and the climate might be totally different. So your measurements only represent a small area. So it's the plateau, and the other region of large area is the ocean around Antarctica, the sea ice. So it's those two regions that I've focused on as a climatologist. This is the political map of Antarctica. Antarctica is not owned by any country, but there are 7 countries that claim parts of Antarctica. The biggest part is claimed by Australia. Oh, Australia is close to Antarctica, so that makes some sense. And this whole region of East Antarctica, except for this little sliver that's the French claim, is Australian claim. And the countries that do claim parts of Antarctica, they put all their research stations on the part that they claim. So for Australia, Casey, Davis, Mawson, and for the French, Dumont-D'Urville. Then there was the Norwegian claim and the New Zealand claim. They don't overlap, but then the other 3 countries all claim the same part of Antarctica. Britain and Argentina and Chile, they all claim the peninsula, and they all focus their research stations in that area. And the U.S. does not make any claim to Antarctica and does not recognize any of the claims, and has established a station at the South Pole that sits on all of those claims. Because they're in the form of wedges of a pie. So in the interior of Antarctica, it is the snow falls throughout the year, and it's so cold that there's no melting. So the snow just builds up year by year like a sedimentary rock, and it compresses under its own weight into ice. When you get down about 50 meters or so, it's compressed into ice, and the air that's in the snow is closed off as bubbles. And the ice just gets thick until it starts to flow, and it flows downhill under its own weight. And it flows then down to the coast. It is still too cold to melt, so it continues to flow out onto the ocean and floating as what's called an ice shelf, which would be several hundred meters thick. And then out at the front of the ice shelf, where there's ocean currents and tides causing cracks to form, and then chunks of the ice shelf break off and float away as icebergs. And that's in contrast to sea ice. Icebergs originate as snow, whereas sea ice originated by freezing of seawater. And sea ice is only maybe a meter thick, whereas the ice shelf the icebergs might be several hundred meters thick. So this, for example, is the front of the Amory ice shelf, the largest ice shelf in East Antarctica. And that cliff's maybe 50 meters high, but of course most of the thickness is below the ocean. And what's in the foreground here is sea ice. In fact, in this case, it's just formed overnight, so it's only a couple centimeters thick. And then icebergs that form from they call it calving. Calving of icebergs, like a cow gives birth to a calf, well, the ice shelf gives birth to icebergs. So they call it calving. And around the continent in the ocean, in fact, an area that's actually larger than the continent, is covered in the winter by sea ice, which almost all melts away in the summer. So this is from satellite data. The area of sea ice at the maximum extent in September at the end of winter, and then the minimum in February. And the amount that melts away is a huge area of the ocean. In fact, it's about as large as South America, the area of the ocean that melts away every year. Well, my first opportunity to experience the Antarctic sea ice was for my first sabbatical leave. So I started teaching in 1982 at the University of Washington. And after teaching for 6 years, then I qualified for sabbatical, meaning I could take a year to do something scholarly. The 7th year, sabbatical, Sabbath, 7th, I guess they're all related. And I decided I wanted to learn about sea ice for 2 reasons. One, because it covers such a large area, has great importance for the climate. And the other reason was I'd been teaching about sea ice for years, but had never seen any. So I wrote a letter to Ian Allison, who is the Australian sea ice expert. Since then, there are many sea ice experts in Australia, but then he was the one at that time. And I said I would like to join him on a ship voyage to study sea ice, and I'd be happy to help out with whatever he had planned to do. And he said, well, no, what I want you to do is bring along your radiation instruments, and we'll measure the reflection of sunlight by different types of sea ice. And I replied, well, we do have those instruments, but unfortunately, I don't know how to repair them. So we need to bring along my student, Rich Brandt, who does know how to repair them. And Ian was able to get berths on the ship for both of us. And he said, you need to come in October, early spring, because that's the time when the air is still cold and areas of open water that are exposed will be forming new ice. So we'll get to sample a variety of different types of ice if we go in October. Now, the voyage that we took, well, here's Australia, and here's Antarctica, and the ship left from Hobart, the capital of Tasmania, and it took this route to visit the 3 main Australian stations and then come back to Hobart. And as you see, we didn't get into any of those stations because this time of year the ice is too thick for the icebreaker was a fairly weak icebreaker, couldn't break very thick ice, but it got close enough for the helicopters to fly off to take in essential equipment and personnel to each of those stations. Now, this is a very remote part of the world. If you ask yourself, where on earth would I go to be as far as possible from Salem, Oregon? The answer is on this map. This is the point, the antipode of Salem, and we came fairly close to that point on this voyage. So the ship voyage started in Hobart, but of course for me, the trip started in Seattle, and it was quite some time before I reached Tasmania. But we did get there. This is Hobart, the capital of Tasmania, and this is actually a picture from the ship at the wharf as we're about ready to leave. Now, we were just doing a round trip for 2 months, but I should say, this is also the location of the Australian Antarctic Division, based in Hobart. There's the ship, and there's the wharf, and there are the friends and relatives of people who are on this ship. So as I said, we're only doing a 2-month round trip, but many of the people boarding the ship there were going to be gone for 15 months, 2 summers and a winter. So this is quite an emotional event for their family to wave them goodbye. Now, we went down the estuary of the River Derwent, and as soon as we emerged into the open sea, we're in the roaring 40s, and the big waves. icebreakers have no keel, so they roll easily. This is how you get, see, I'm doing the ocean first, because you have to get to Antarctica, and then later we'll talk about the continent. So, left, right, up, down, left, right, up, down. Oh, can we turn off these lights that are in the front? They're kind of shining on the screen. Leave the other lights on. You could leave the other lights on. Well, or maybe you don't have to, but it was just those front ones I wanted to. Yeah, that's fine, I think. Or is that okay? Do you want them off too? Yeah, okay. So, of course, there were consequences inside the ship. Left, right, left, right. So we were all happy. After about 7 days of this, we were very happy to get into the ice, because the ice damps the waves, and everybody who was seasick could now come out and get off their bunk. And okay, well, when the ocean water cools to the freezing temperature, which because of the salt content is -2 Celsius, then further it doesn't cool anymore. Instead, further cooling results in freezing instead of lowering the temperature. And at first what you get is just small crystals that form in the water, and they form a slurry that damps out the smallest waves. So you can hear the smallest waves, and here they're damped out. So that's how you can see that there's ice there. In fact, it kind of looks like an oil slick. And in fact, it's called grease ice because of that appearance. So here's grease ice. And then over time, the crystals get more numerous. They start aggregating together into clumps about the size of cornflakes. And then those clumps aggregate together to form what are called pancakes, maybe about 1 meter across, and they're bumping into each other, so the edges get raised. This is the kind of ice that forms where there's significant wave action when it's first forming. These pancakes then will aggregate together and form a uniform sheet, but in the form of pancakes, they're very easily moved about, and the ship has no trouble just plowing right through them. When it does, though, sometimes one pancake will ride up on top of another one. So that's called rafting. And so what that means is that when this whole scene would freeze together, then the ice here would be twice as thick as the ice here, because there's 2 layers of pancakes. And each pancake might be 30 centimeters thick. Now, if you don't have wave action, if you have a calm area of the ocean, then that's just exposed as open water, then instead of pancakes, what forms is a uniform thin sheet, which is given this Russian name. It's called Nilus. And then within a few days after forming, you're almost certain to get some snowfall, and thereafter the surface just looks like snow. Until then, the amount of sunlight reflected depends on the ice thickness, but then once you've got snow cover, it really is just snow covered. This is the most common ice type that we found in October. This is ice that formed early in the winter, and it had all winter to grow, and so it was about 1 meter thick or so, called first-year ice. If it lasts through a summer, then it would be second-year ice. And so here's first-year ice looking from a helicopter. It's called this chunk of ice called an ice flow, and there are divergent ocean currents that have caused a crack to form. And if the crack gets big enough to lead a ship through it, then it's called a lead in the ice. Now here's, you can look at a long history here. There was an ice flow. It broke apart, and this lead formed, and then the air was cold, so new ice formed in the lead. This is new ice, and then it started closing up. So you're getting rafting there. So where the ice is twice as bright, it's twice as thick. Now, out at the margins at the northern end of the sea ice zone, where the ice is coming into contact with the open ocean and there's significant wave action, then the waves splash onto the ice and mix with the snow and make a slush surface. So this is ice that's in the process of decaying. A good way to estimate the ice thickness is to go down on the lower deck of the ship as it's pushing through the ice and breaking the ice and turning some of the ice flows on the side. So you can see this ice is about 1 meter thick with maybe 15 centimeters of snow on top of it. And this ice also contains life. You can see some sort of brown color in there. That's algae that are growing in the ice. The Antarctic Ocean is a fairly prolific region for biology. And here's an overturned flow with a lot of brown color in the ice. Now, the ice that is attached to the coast, it's fastened to the coast, and so it's called fast ice. That ice is not mobile, and so the algae that grows on that is just growing as a thin layer on the bottom. And here's one that's overturned, so it's all pretty pure ice, except on the bottom it has this this thick layer of algae. And the sea ice zone is beautiful, especially at sunset. And you look at these scenes, and they are ephemeral. This scene has never occurred before and will never occur again. The ice is always in motion. Well, our mission was to measure the reflection of sunlight. So what we do, we use an instrument which is somewhat like a light meter for a camera, except we have a filter wheel that measures, so we can select different wavelengths to measure, and we turn it to look up, and we measure the sunlight coming down from all angles, and we turn it over, and we measure the sum of all the radiation at that wavelength coming up from the snow at all angles, and that ratio is called the albedo. Albedo, it's comes from the Latin word albus, meaning white. It's the same root as albino or alp. So we've got the downward flux from the sky, and we've got the upward flux, the reflected, and so the ratio is the albedo. And that's a number between 0 and 1, or 0% to 100%. And some typical values, oceans are pretty dark, only 7%, and snow is the brightest surface, 80%, and the planet as a whole, that picture I showed you from the astronauts, 30%, most of which is due to clouds. Now let me just ask you, do you like this microphone? Or is this one better? The handheld is better? This one's better. You like this one? Okay. Okay, so, did I turn, oh, there it is, okay. So, for most of the ice types that we wanted to study, they were too thin to support our weight. So there were two options for making our measurements. We could fly off in a helicopter and open the door and thrust our radiometers out the door and turn them to look up and look down. I had a bubble level on the inside to level them. And the other option was to hang in a basket from the ship's crane and be lowered down over the ice. If the helicopters were busy and the ship wasn't moving, we could do that. And believe it or not, this experiment was commemorated on an Australian postage stamp. There's Rich on the left with the data logger, and that's me on the right with the And in the year 1997, you could go into any post office in Australia, and for $1.05, you could buy this stamp. Of course, I bought a lifetime supply. The advantage of being in the basket was we could be lowered down to the ice and collect a sample of the ice, and then look at the structure to see if we could explain the albedo measurements that we were making. Problem, though, with the basket is that when we looked up, our instrument was not just looking at the sky, it was also looking at the hook and the crane. So we had to make a correction for that, which we did work out how to do. But then 8 years later, when we went back, we minimized that correction by using a longer rod. When we had 2 days at Mawson Station while the helicopters were busy, and we went off to make measurements on the fast ice of the snow albedo. And well, penguins are curious, and so they noticed that there was something strange going on there and came over to have a look. These are the short ones. These are the adelies, and the other species, the tall ones, are the emperor penguins. And after a while, we acquired quite a crowd that were curious about what we were doing. After a while, they started getting impatient and really curious, so they sent a delegation over to interview me. And at first I didn't take them seriously, but they were quite insistent, and so I said, well, look, if you really are interested in this project, we'll show you how to press the buttons, and you can take the measurements this afternoon. And the Adelie said, who, me? I'm not here. Not here to work, I'm just here for fun. And the emperors, they're very regal animals, and they pretended not even to be interested, but actually they were interested. So I leveled with them. And I said, okay, it's okay if you just want to stay here and watch, but we're making measurements of clean snow, so please don't go polluting it like your friend over there is doing. And indeed, they did just respect our work all afternoon. They stuck around and never once walked under our radiometer. Okay, so that work resulted in this paper, and then 8 years later, that project was so much fun that my next sabbatical, I also went with the Australian Antarctic expedition, filled in some more of the blanks on our table, and were able to make a comprehensive map of surface albedo for the Antarctic sea ice zone. And then I had a student who combined that data with measurements on clouds and got the relative importance of the clouds and the sea ice for the solar energy budget. Okay, now for the rest of this part of the talk, let me first, I need to point this out. I mean, you know about what's going on with the Arctic sea ice, and there's important differences in climate change, what's happening in the Arctic and the Antarctic. Arctic sea ice area has declined rapidly since 1980. Well, we have accurate measurements since 1979, when the satellite was launched that could monitor the Arctic and the Antarctic sea ice. Antarctic sea ice area has not changed much. It increased slightly over that 35-year period. Until last year, there was a dramatic decline, which was maybe an anomalous event having to do with El Nino and other things. But so why the difference? Why is the Arctic sea ice rapidly declining, but the Antarctic not? Well, there's a clue in, this is a picture of the Arctic sea ice in the summertime from a helicopter. This is not from me. I've never been in a helicopter over the Arctic sea ice. But what you see, this is in the summer after all the snow is melted, and the melted snow has formed puddles on the ice. So what's white here kind of looks like snow, but it actually is just drained ice that is fairly bright. So in the Arctic, the ice is fairly thick, maybe a couple meters thick, and it gets a fairly thin snow cover. And then in June, that snow melts, and it forms puddles in depressions on the ice. And then later on in the summer, as the ice warms up, channels form and allow the meltwater to drain, and the ponds drain in August. In the Antarctic, Arctic Ocean has thicker ice, thinner snow than the Antarctic. Arctic ice melts from the top down, forming puddles. So it melts because of sunlight, and then the puddles are dark, absorbs even more sunlight. The Antarctic sea ice melts from the bottom up, remaining snow covered. You don't see puddles on Antarctic sea ice, and there's been papers written about try to explain why that is. The temperatures are lower, it's cloudier, you don't get as much sunlight, it's colder. And also the ocean is warmer. The Arctic Ocean water under the ice is fairly cold, and the Antarctic sea ice is at lower latitude, and there is water there that can melt the ice from below. In the winter, the air temperature is cold enough so it counteracts that warming from below. But in the summer, what happens is that the warm ocean water melts away the ice from the bottom and melts it all the way until the snow no longer has any ice to sit on, and then it falls into the ocean. So when it loses its platform, then it falls into the ocean and melts. So this slight increase in the sea ice area in the Antarctic is actually related to this process, in that the warm ocean water is having difficulty accessing the bottom of the ice. Now what can do that is if the surface water of the ocean is fresh water, then the salt water is at a higher density and it can't convect to get up to the top of the ocean. And the surface water has been becoming more fresh in the Antarctic Ocean. Now, one reason for that is related to what I'm going to be talking about some later on, and that you probably know about, that the Antarctic, some of the ice shelves in Antarctica have been breaking up. Icebergs been floating away, and in fact, glaciers speeding up because the ice shelf is no longer there to buttress them. And so the production of icebergs has increased. And the icebergs are freshwater, and when they melt, they freshen the surface water. So temporarily, they're making it more difficult for that warm water to come up. In fact, the water down at a couple hundred meters is warming in the Antarctic. It's not getting to the surface where it could lose its heat by melting sea ice, or not as much. So that's at least part of the explanation for why the Antarctic sea ice is slightly increasing. And also, because the ocean is the main control of the melting, it's a much slower response to global warming, because that water that's coming up is part of the north-south circulation in the ocean, where you have sinking in the Arctic and then flow all the way down along the bottom of the ocean and then up in the Antarctic, and maybe 1,000 years old, that water that's coming up to melt the sea ice. So it's not seeing the result of recent climatic warming. Okay, but of course, as global warming continues, the whole process of melting may change in the Antarctic. Okay, well, I've got a few more minutes before this section of the talk is over, so I'll bring up another topic about the ocean, which is the colors of icebergs. Well, they can be white, they can be blue, they can be green. This is the kind of picture you're probably familiar with. This is what ordinary icebergs look like. They're mostly white, like snow, but they're maybe tinged slightly bluish. But over the years, there have been occasional reports of green icebergs. The most famous, of course, is from Coleridge's Rime of the Ancient Mariner. Ice mast high came floating by, as green as emerald. And that was 200 years ago. Green icebergs first appeared in the scientific literature 1933 in this article by Wardy and Kemp. And since then, there have been occasional reports of green icebergs, individual green icebergs worthy of writing a little note. And on some icebergs are striped, where they have dark green regions surrounded by ordinary white glacier ice. In fact, sometimes the green ice is so dark that it's called black, but if you look closely, it's actually green. Well, when we were on our sea ice voyage in the vicinity of the Amory ice shelf, we were in the region. It turns out, is the most prolific producer of green icebergs. And so here's the Amory ice shelf in around 70 degrees east longitude in East Antarctica, and the two Australian stations are on opposite sides of the Amory ice shelf, and the crew members at those stations often see green icebergs. They call them jade bergs. And we were docked on the fast ice for 2 days near Mawson Station, and we were right near this iceberg that appeared that part of this iceberg was green, although a lot of it's hidden by snow. There's blue ice on the left, green on the right. So here's the boundary line. There's blue ice, fairly bright because it has lots of bubbles. And then there's this green ice, which is very dark, quite clear, apparently lacking bubbles. And this was our interpretation. Bubbly blue-white ice on the left and clear green ice on the right. This is, if you remove the snow, this is what we thought it would look like. And then we were able to climb up onto this iceberg and make some measurements on the green part of it. You can see some contrast between the blue sky and the green ice. This ice was not very green, but when we got up there, the most amazing thing about this ice was not its color, but rather its clarity. It had no bubbles. You could look deep, deep, deep. There were these cracks, so you move your head back and forth, and you could estimate many, many meters deep into the ice you were looking. So immediately we knew this ice did not form from snow, because snow is full of air and the air gets closed off into bubbles, and so glacier ice always has bubbles. And this ice must have formed by freezing of liquid water. What kind of liquid water? Well, we drilled at a core, measured the oxygen isotopes. That told us this formed from seawater. It had the isotopic composition of seawater, not snow. So, and then we made a connection to this paper that had been published some years before about bottom freezing on the Amory ice shelf. The drilling through the Amory ice shelf, there was glacier ice, and then the isotope suddenly went up to the seawater value, meaning that the bottom part of the ice shelf was frozen seawater. So there was this whole literature about, on other ice shelves too, about freezing on the ice. Well, the ice shelf is spending maybe hundreds of years in contact with the ocean. So there's melting that goes on, and there's also freezing at the bottom of an ice shelf before icebergs break off. So there was this whole literature about freezing to the base of ice shelves. And then there was this separate body of literature about green icebergs. And we made the connection that actually green icebergs, this is where they come from. They come from this freezing of the base of ice shelves. Now here's a modern paper showing a cross-section. Here's the ice shelf. Here's the bedrock. And depending on the ocean currents, if the ocean water flows in here down to the grounding line where the ice sheet separates from the bedrock, then that water is going to melt away enough ice to cool itself down to the freezing temperature. The freezing temperature depends on the salinity and on the pressure. You know about pressure melting, that if you increase the pressure, the freezing temperature decreases. And in the Amory ice shelf, the grounding line is quite deep, 2,400 meters, and the freezing temperature is minus 3.7 Celsius. Now, as that water then, that's at that temperature, flows up under the ice ceiling, it's down now, it's up to at lower pressure now, and it finds itself supercooled. So ice crystals form in the water, and then they float up, and they accrete to the base of the ice shelf. And that ice is called marine ice. Not a very descriptive name, but the name is different than sea ice for two reasons. One is it doesn't contain bubbles because air is more soluble in water at that depth. Also, it's desalinated. There's hardly any salt, and it's somewhat of a mystery. How does it get rid of all the salt? Anyway, if that marine ice survives to the front of the ice shelf, then when an iceberg breaks off, it'll consist of two parts, the upper part, glacier ice, and the lower part, marine ice. And the marine ice is hidden below the waterline, but if the iceberg is small enough, it may capsize, and the marine ice gets exposed to view. And that's what we have in this situation. We did measure the spectral reflectance of this ice, and as a function of wavelength, the reflectance, well, normalized reflectance, blue ice would peak at about 470 nanometers, and the green iceberg we measured had a peak in the green. So it was not an optical illusion. This is inherently green ice. And the explanation for that, you need something other than water in the iceberg. You have to add something. Well, see, ice has an absorption coefficient, increases from the blue to the red, and if you add something that goes the other way, that absorbs more blue and less red, then you can shift the minimum absorption over. So if you've got something that's yellow, ice is inherently blue, but if you put something yellow, then you know yellow plus blue makes green. So that's what happens here. It could be dissolved organic matter, algae, particulate organic matter, or iron oxides. You know, red iron oxides, they also absorb ultraviolet and blue, but not red. That's why they look red. So any of those added to ice will change the color. Now, we published this paper saying that green icebergs are formed by freezing to the base of Antarctic ice shelves, and at the time we thought it was organics, but now we think that the iron oxides may be at least as important, maybe more important. Now, about the same time, there's a German group that also came to the same conclusion, that green icebergs are originating from freezing to the base of ice shelves. And you see, their iceberg was greener than ours. And so when National Geographic wanted to write a story about green icebergs, I told them to get their picture from the Germans. Okay, well, then when we went back 8 years later, we had another opportunity to experience marine ice, and we discovered, well, it's not always green. And if the water that it's freezing from is really pure water, then you'll get blue ice instead of green ice. And this picture actually has 5 different types of ice. This is an iceberg that's turned over at about 70 degrees. This was originally horizontal here, the boundary between the glacier ice and the marine ice. We're standing on sea ice that's mostly snow-covered, and then there's an ice cloud. Well, why is it blue? Well, it's those cracks that scatter light. Red light penetrates about 2 meters before being absorbed by ice. Blue light about 200 meters. So if you have a long distance of travel of the light through the ice, more than 2 meters, the red will be gone, the blue will survive, but it has to find some way to turn around, and it can refract at those cracks, come back out to your eye. Now, ice cubes in your refrigerator have no color, and that's because they're too short. They're much less than 2 meters, and so both the red and the blue survive, and they're just clear. Snow is white because snow reflects light by refraction. Light comes in and it refracts at snow grains, and maybe even if it has to go through 100 or 200 snow grains before getting turned around to come back out, in the process it's passed through only a short distance through ice, maybe a couple centimeters, and so both the red and the blue survive. So snow is white. And ordinary icebergs of bubbly glacier ice are bluish white. They're intermediate. Yeah, here's a picture of some bubbles in glacier ice. Snow gets compressed into ice, and the ice contains bubbles. here's the boundary line, the glacier ice and the marine ice. And we were able to climb up onto this iceberg too, and make our albedo measurements. And there were different parts of this iceberg. Some were blue, some were green, some were yellowish green. And when we plotted the albedo as a function of wavelength, the brightest was the glacier ice, and then the three kinds of marine ice that had their peaks at different wavelengths. So summarize, pure ice is blue, organic matter and iron oxides absorb blue and ultraviolet, shifting the absorption minimum to longer wavelength. Or more simply, if the source water is blue, the ice will be blue. If the source water is green, the ice will be green. Oh, and then there's stripes on some icebergs where you have glacier ice and then you have stripes of marine ice. And what would cause that is that as the ice shelf is separating from the bedrock, tension cracks form at the bottom, crevasses at the bottom, and then seawater will immediately flood up in to the crack and freeze. And you get a stripe. And if you look on the web for striped icebergs, you'll find plenty of pictures. This one is from National Geographic. Yeah, well, let's see. I guess I'm out of time here. There are some ways in which marine ice is important, and one is that they contain all this stuff. It's like, has a lot of iron, all this debris that's in the marine ice. And iron is the limiting nutrient in the Southern Ocean. And this glacier flower, without marine ice, it would just fall to the bottom of the ocean under the ice shelf. But the marine ice, in the form of an iceberg, can be a delivery mechanism. It can carry it out into the ocean, melt somewhere far away, and deliver iron as a nutrient for the plankton in the ocean. So actually I'm involved with the Australians in developing a proposal for doing a dedicated study on icebergs. We, in the past, we always thought they were just an object of exotic curiosity, but now we think that they're worth a study. Some of us do, anyway. Okay, questions?
Yeah, my name is David. I'm an ex-seaman, but I've heard, but I don't remember how much higher this level of the sea would be if the ice at both poles melted.
Yeah, the so-called sea level equivalent amount of ice in Greenland is about 7 meters, and Antarctica is about 65 meters. If you took all the ice off Antarctica and put it into the ocean, the sea level would rise 65 meters. And, well, some millennia from now, that may be what we'll have. Yeah. Oh, yeah, well, later on I'll talk briefly about Greenland. Yeah, but both Greenland and Antarctica are losing mass at present. Yeah. It'll be a slow process to put all that ice into the ocean.
Oh, this is Paul. The pictures of the ship heaving and going up and down different and random places. I was on a destroyer in Western Pacific typhoon, and the ship did the same thing. And all I remember is along the scattered throughout the ship were garbage cans to allow the crew to throw up as they passed by. I don't know if your ship had any of that.
Yeah. Yeah, I was seasick well, they gave us medicine to take, which kind of puts you to sleep. And but even with that medicine, I was seasick for about 2 days. And then I think the way I got over it was I stopped insisting that walls were vertical and floors were horizontal. And I started actually taking advantage of it. Instead of struggling to walk up the corridor. I just wait until it was downhill, and then I just slide down. And then instead of struggling to pull a door open, waited until it turned toward me, and then just open the latch, and it falls open. So you can just be patient and adapt.
I'm trying to get a feel for the height of the little penguins and the big penguins. These are the little ones, right? And they're only about from your knee to your waist? Okay. And how tall are the monarch or the empire?
Yeah, those emperors,
Emperors.
they're so, you know, they're maybe almost, I don't know, 4 feet tall. They're so human-like, standing on 2 legs, that sometimes just without thinking, I felt like, you know, going out, holding my hand out, and, you know, I did that sometimes, but they did not want to shake hands. They backed away.
From your pictures, it looked like it was fairly warm. What were the temperatures you were dealing with?
Yeah, well, this picture, this is kind of an unusual day in that there was no wind. Wind makes all the difference. The sun is bright. If there's no wind, then you're, even though the actual air temperature in the shade is probably, well, I don't even know what it was there, but it was well below freezing. There was no melting going on the snow, but it felt warm enough to take off my hat and my gloves. Yeah.
Hi, this is Irene. I'm visualizing this thing about there's not as many clouds around the North Pole, so it melts the top of the ice, and then it goes underneath and sends water down to the South Pole and freezes underneath.
It melts underneath.
Oh, melts
Yeah.
underneath. And
Yeah, well, that
it's the opposite. And so I'm just wondering, how long does that take for the water to get there? And what's this all about? Is this
About 1,000 years.
1,000 years?
It's just part of the, well, yeah. The upper part of it's called in the Atlantic, it's the Antarctic Meridional Overturning Circulation, AMOC. And the Gulf Stream is part of that. You've got water coming at the surface going north, and then it's salty enough that as it gets cold, it's able to sink all the way to the bottom of the ocean. Not all the way in the Arctic. It's somewhere in the North Atlantic, around between Norway and Greenland, sinks to the bottom of the ocean. And then there's this current down at the bottom of the ocean that carries water southward all the way across the equator and then comes up in the Antarctic. It's also called the global conveyor belt. Yeah, I think it's about 1,000 years.
My name's Roger, and I was interested in your comment that Antarctica is usually covered by clouds when seen from space.
Well, the Antarctic Ocean is covered by clouds. The Antarctic continent is only half covered and the clouds are thin.
I see, and they must also be very high because I've read it's very dry. It's a desert in Antarctica, and it must be mostly ice or something because there's no precipitate.
Well, I'll be talking about that after the break. I'll be talking about the climate of the continent, including clouds and snowfall, and yeah.
Thank you.
Yeah.
Will you be talking about the thinning of the ozone layer over Antarctica? Does that affect your measurements on ice?
Actually, I could. It's not part of my talk, but I do have a slide at the very end that I could add in about that. Since you asked, I will. It's an interesting topic, yeah, about the ozone hole. Yeah, the ozone is, well, yeah, it's very, actually, there's a lot of interesting stories related to that. The ozone is destroyed by reactions that occur on ice crystal surfaces. So on clouds in the stratosphere, normally the stratosphere is too dry for clouds, but the temperatures get cold enough in the Antarctic winter that you get clouds forming in the stratosphere, and they serve as a catalyst for the destruction of ozone. The chlorine oxide molecules will react with ozone, and they react much more rapidly on the surface of an ice crystal. And so you need that surface, and you need sunlight. So you've got the surface in the winter, but you don't have sunlight. And then you've got the sun comes up in September, and in October is when the ozone gets to a minimum. And then then it gets warm, the clouds evaporate, and then the ozone recovers. So it's a seasonal thing, September, October, November, and by December, it's all recovered. Although sometimes you get pockets of ozone-depleted air that'll come up over Australia or New Zealand in the early summer when the people are lying on the beach sunning themselves, and they can get sunburn because of that. Yeah.
Okay, why don't we take a 10-minute break, reconvene at 25 till. Thank you very much.
Okay. Okay, now the topic is climate of the Antarctic ice sheet. So we're going to go on to the continent now. And what do I have here? Okay. As I said, for climate, the most important areas are the plateau. There's all these stations around the coast, and then there's a few that are in the interior. The South Pole Station and Bostock, the U.S. station, the South Pole, the Russian station of Bostock. Those are the longest continuous records from 1956, so a little over 60 years now. South Pole Station has been operated. And I'll also show some results from Bird Station to represent West Antarctica, and maybe Plateau Station. So topics: first temperature, then clouds, snowfall, and wind, and drifting snow. This is the South Pole Station when I knew it. Most of the buildings are under this dome, which is now gone. They've built a new station, and I haven't seen it. The dome, and then there's the archway, and there's some other buildings. It's a very important station. It's right at the South Pole, and so its weather records are often used to represent the entire latitude zone 80 to 90 south. Yeah, well, this is the pole right here, this copper pipe. It's established by the Geological Survey, and every year on January 1st, there are two employees of the Geological Survey come down from Reston, Virginia, and they have to set a new copper pipe because the ice is flowing about 10 meters a year. And sometimes people will put up signs pointing to their hometown or to another station, and this sign there, it tells you the direction to yonder. Well, often the South Pole is described as a unique location because it is right on the Earth's axis of rotation. And for the astronomers, that's true because, it is a unique and usefully unique location because the stars stay at the same elevation. They don't go up and down over the course of a day. So it's a good place for astronomy. But for climatologists, the beauty of the South Pole is not that it's unique, but that it's ordinary, that you can make measurements there and the climate is probably the same 500 miles away. So there's this weather station at the South Pole with 4 meteorologists in the summer and 2 in the winter. And they keep the thermometers and the anemometers running, and they launch balloons with radiosonde instruments to measure temperature and winds through the atmosphere twice a day in the summer and once a day in the winter. This is a summer picture. There it goes. The station was established in December 1956, and Paul Seipel was the first station science leader for the winter of 1957. And he published this article afterwards in National Geographic, Man's First Winter at the South Pole. And when he came back from Antarctica, he gave a lecture tour. And fortunately, my father took me to one of his lectures. It was in February 1960. He gave a lecture at Purdue. And I remember sitting up there in the chemistry building at Purdue and Paul Seipel showing his slides. And that's when I understood that it was actually possible to live at the South Pole and to spend the whole year there. 32 years later, I followed in Paul Seipel's footsteps, and I was the station science leader for the winter of 1992. With a crew of 22 people. We were in isolation for 8.5 months. A very unusual year. I would wake up in the morning without any fear that I was going to run into somebody that I'd forgotten their name. And yeah, so the other important station I've also spent some time at is Bostock Station, the Russian station in the interior. Now, Bostock is famous for 2 reasons. Who knows? 1 or 2 reasons why Bostock Station is famous. Well, it was the site of the first deep ice core in Antarctica. At Bostock, it's in the interior of East Antarctica. Actually, the word Vostok is the Russian word for east, but that's not why the station was named Vostok. It's actually named after a Russian ship that was called the Vostok from years ago. Anyway, it snows about that much in a year, gets compressed in about that much ice, about 1 inch of ice. So a 10-foot long core of ice represents 100 years. And so because the snowfall rate is so low there, they can drill down and get a record of climate back. Went back about 300,000 years. And this is this is the drilling rig for drilling the ice core. The other reason that Vostok Station is famous is because they have set the world's record for low temperature. And so for a climatologist, the first tourist attraction at the Vostok Station is the thermometer at the weather office. And this is the thermometer that recorded the temperature of minus 89.2. So you go into the weather office and you look in the logbook of monthly summaries and turn to page 1983, and these are the months: January, February, March, April, May, June, July. And the first is the average temperature, minus 73.8, the highest temperature, and the lowest temperature, minus 89.2 on the 21st of July. And that's a world record for a weather station. Now, actually, there are places that are colder. There's just no station there. And from satellite measurements, they've found a temperature. So there's Vostok, minus 89. Oh, and by the way, in Fahrenheit, it's minus 128 or something. So the lowest temperature they find from satellite is up at this higher location at Dome Argus, and they've gotten as low as minus 93.2. Okay, so it's cold in Antarctica. These are contours of annual mean temperature. The East Antarctic Ridge, the high region of East Antarctica, minus 55. South Pole, it's minus 50. And this is average. If you look in July, you see I've highlighted the freezing temperature, 0 degree contours way out in the ocean, go between South America and Antarctica. And even in January, the contour of 0 degrees is out in the ocean, except it goes through the western Antarctica. So the western side of the peninsula is above freezing in January, the warmest month of the year. Okay, now comparing the Arctic and the Antarctic, mean annual temperature, North Pole minus 20, South Pole minus 50. Why is the Antarctica colder than the Arctic? And there are 3 main reasons. One is what we call zonal flow in the atmosphere in the ocean. If you go around Antarctica at 60 degrees latitude, you will not hit any land. And Antarctica is sitting almost symmetrically on the pole, And the winds and the ocean currents just go round and round. They don't bring much heat into Antarctica. Whereas in the northern hemisphere, you've got these continents that break up the circulation and force the ocean currents can't go round and round. And so like the Gulf Stream comes up into the North Atlantic and warms the Arctic. So it's that more zonal flow in the Antarctic going around in latitude zones instead of up and down from low latitude to high latitude in the Arctic. And the high elevation, it's also because Antarctica is on a continent, the Arctic Ocean is an ocean, so it's at sea level. The Antarctic continent with the ice sheet, it's at high elevation, so it's colder from that. And also the fact that it's snow covered throughout the summer keeps it cold because it has a high albedo, reflecting about 83% of the sunlight in the summer. Gets a lot of sunlight in the summer, but reflects almost all of it. Okay, so a lot of the figures and tables I'm going to show are from this encyclopedia article that some of you have read or printed out. In this table, I've compared 5 stations, 2 for East Antarctica, South Pole and Bostock, 1 for West Antarctica, and then 2 coastal stations. Mirny at latitude 66, and Little America, or Framheim, that's where Amundsen started his trek to the pole at 78 degrees latitude. So South Pole and Bostock, well, so summer temperature is about 5 degrees colder at Bostock, and also the winter temperature is about 8 degrees colder. And that they're both the same distance from the coast, but Bostock is at higher elevation. That's probably explains why it's colder. And there's that extreme minimum temperature at Bostock, and the maximum temperature is well below freezing, minus 14 at the South Pole, and that's for 60 years of data. And I think we can be confident that there's been no melting at the surface at the South Pole, probably for at least 14 million years. That's when Antarctica developed the ice sheet to its present elevation. Now, on the coastal station, the average summer temperature is below freezing, but it's close to freezing, so the extreme temperatures get well above freezing. And in West Antarctica, Bird Station got almost up to the freezing point on one day. Now, I do have an asterisk there on the South Pole record because that was at the situation as of the time I wrote that encyclopedia article in 2011 or 2010. And that record was set in December 1978, but there's a new record high now. Minus 12.3 is the new record high at the South Pole. So as I said, there's not much melting. This map shows where there is melting from satellite microwave measurements, number of days of melting. And where there is melting is on the ice shelves, which are down near sea level, the Ross Ice Shelf, the Filchner-Ronne Ice Shelf, and the Amory Ice Shelf. And then on the peninsula, there's considerable days of melting. But this is only 1 to 7 days, and so it's only around the coast and some number of days in the summer where there will be some melting. Now, what did I want to say about this? Maybe something about the cold temperatures, minus 89, minus 129 Fahrenheit. When these very low temperatures occur at the surface, it's actually warmer up in the atmosphere. You have a temperature inversion. You know, normally as you go up in height, the temperature gets colder. You go to the top of Mount Hood, it's going to be colder than in Salem. And if it's reverse of that, if the atmosphere is warmer than the surface, then it's called an inversion because it's the inverse of what you normally expect. And inversions are very normal in the Antarctic winter. They also occur in mid-latitudes in Oregon and Washington in the winter at night. Not every night, but it's when you don't have sunlight to heat up the surface, and especially if it's clear, you don't have clouds, then the surface emits radiation and cools by radiation, by emitting infrared radiation. And the Antarctic is a much more extreme situation that persists through the winter. So here's, as a function of height or pressure, starting at the surface at the South Pole, temperatures increasing, and then up a few hundred meters, then it starts decreasing. And then expanding that plot so we can actually see what's going on near the surface, increasing temperature from -60 up to -40 or 38. And then it's fairly constant, and then eventually it starts decreasing. So the explanation for that, the snow surface is a very efficient emitter of infrared radiation. And the energy budget, there's no sunlight in the winter, so the main things that you've got are emission of radiation from the surface upward and emission downward from the atmosphere. And they come over time into equilibrium. And the atmosphere is an inefficient emitter. But the surface is an efficient emitter, so it has to cool down so that its efficient emission from a low temperature balances the inefficient emission from a high temperature. And that's, I had the equations on here, but I removed them for this talk. So that's the explanation. And in fact, the most extreme inversion is right near the surface, just the first 20 centimeters above the surface. Going up 20 centimeters, the temperature is already 1 degree warmer than the snow surface, the temperature in the air. Okay, well, this is the strength of the inversion. It reaches about 25 degrees Celsius in the East Antarctic Plateau and maybe 5 degrees on the coast. So it's mostly in the interior where it's really extreme. Now, one thing that you can't do at the South Pole is look at a daily cycle. So to look at the daily cycle, we go to Dome C, which is at latitude 75 degrees. And in the summertime, the sun, although the sun doesn't set, it goes down quite close to the horizon. And then at noon, it's pretty high. So there's quite a daily cycle in the heating of the surface. And an inversion develops at night, and it gets destroyed by the sunlight during the day. So here's as a function of height, this is above sea level. The surface is actually at 32 something meters, 100 meters. So at night you have this inversion, and then in the afternoon it warms up to by maybe 10 degrees. But above a few hundred meters, it's really no difference from day to night. So it's just this near surface thing going back and forth as the sun goes up and down. These measurements, the lower part of these measurements were made from a tower. We had thermometers on this tower that went up to 32 meters at Dome C. There was also a tower that I used at South Pole Station during my winter at the South Pole Station. So you might wonder what it's like to work and live at the South Pole Station, and if I have to go up onto the tower at a temperature of -67 and spend an hour up there, then it's important to be dressed properly. And these are the raw materials, and this is the finished product. And the key thing about working outdoors in the winter at the South Pole is you have to not mind being clumsy. So wearing 5 pairs of mittens, if I climb slowly up to the top of the tower and I've got to adjust something and my wrench falls down into the snow, then I slowly walk down and I pick up the wrench and I come back up again. And I don't complain, I don't curse, I just do it. Okay, now these are staying with the surface temperatures, the air temperatures at the surface. This is the annual cycle actually going through more than a year, October, November, and then up to the next year. And this temperature here in Celsius, the solid line is the average of the daily temperatures for 20 years of each day. So you see the temperatures rising rapidly in October and November. The sun comes up, clears the horizon on the September equinox, and then there are 2 months of spring, and then December and January are the warmest 2 months, so that's what we call the summer. And then the temperature drops in February and March, and that's what we call the autumn. And then there's 6 months of winter. So there's a lot of peculiarities here. The first thing I want to point out is the maximum temperature comes only 8 days after the summer solstice. Now compare that to other continents. Now, what day of the year here in Oregon do you get the maximum sunlight? Okay, I'm hard of hearing, but it's in June. And when in June? Yeah, right. The 21st of June is the maximum sunlight. And when is the highest temperature on average? You're saying August. Okay. Well, typically on continents, it would be sometime in July, late July. So the typical lag of temperature behind the sun is on the order of 25 or 30 days. So you peak it takes a while to warm up the ground, and so the highest temperature comes like a month after the June solstice. Whereas at the South Pole, it's only 8 days after the December solstice that the temperature peaks. And the reason for that is that instead of a wet soil surface like you have here, you have snow, which is full of air. It's a very good insulator. So you don't have to conduct a lot of heat down to heat up a lot of snow. The upper snow just heats up rather quickly. So it has the shortest lag of anywhere on Earth of the peak temperature after the summer solstice. Another thing to look at is, well, as I pointed out, you've got 6 months of winter, but the lowest temperature is not, it doesn't look like, you'd think July, the middle of winter, would be the lowest temperature. But in fact, as soon as the sun sets on the March equinox, the temperature stays about the same for the next 6 months until the September equinox. It's called the coreless winter, the winter without a core. So what you have first of all, there's no sunlight for 6 months, and you've got a loss of infrared radiation to space, and that's balanced by an import of heat by warm air flowing in toward the continent in the middle troposphere around 6 kilometers elevation and sinking over the continent. And that import of heat by the atmosphere is apparently maintained rather constant through the winter and keeps balancing that infrared radiation so the surface doesn't have to cool more. And I think the reason for that is that Antarctica is surrounded by a vast ocean whose temperature out beyond the sea ice zone, the temperature doesn't change much from summer to winter in the latitudes 40 to 60 degrees. So that's the coreless winter. Next thing to notice is that these points, I should have said earlier, the points are the individual daily temperatures for 1 year. And what you see is that in the summer, the day-to-day there's small day-to-day variability compared to the winter, where it may, change by 20, 30 degrees from one day to the next. And what's responsible for that is that in the summer, you don't have a temperature inversion. The surface heats up and the temperature is rather constant for the first couple hundred meters. In the winter, you develop this strong temperature inversion, and anything that can destroy that inversion, anything that can bring that warm air down to the surface, like if you have a windstorm that mixes that warm air down, then suddenly the surface air temperature will warm up. The other thing that can do it is if a cloud comes in, because clouds, like snow, are efficient emitters, and so interaction of their radiation will cause them to acquire the same temperature. And I observed one extreme example of that was on the 8th of September, 1992, that we had 2 thermometers on the tower, one at 2 meters and one at 21 meters, or 1.8 meters and 21 meters. And here, there was a difference. This is the most extreme inversion that I've ever seen. 19 degrees Celsius difference between the bottom of the tower and the top of the tower. The bottom was minus 63, and you climb up to the top of the tower, and it's minus 44. And then a cloud came in. And over the next 7 hours, the temperature at the top didn't change much, but the temperature at the bottom rose until there was only a 3-degree difference. So that's the destruction of an inversion by a cloud. And you may have noticed, maybe you didn't notice, that some of these points of individual days were at temperatures below minus 73.3. Anybody notice that? Anybody know what's significant about minus 73.3? Well, minus 73.3 Celsius is minus 100 Fahrenheit. And when, in the winter, usually every winter, sometime the temperature gets that low. And when that happens, there's a special ceremony that we do at the South Pole. It's called the 300 Club. So what you do, you heat up the sauna to plus 200 Fahrenheit, and you heat yourself up in the sauna until you can't stand it any longer, and then you run out of the sauna naked, down the hallway, out the door, down the stairway, out through the entrance tunnel, around the pole 3 times, and then back up the stairs and into the sauna. And so you've gone from plus 200 to minus 100. So you've gone through 300 degrees. And oh, I should say we do wear shoes for this. And so I'm a member of the 300 Club. And in fact, it has been recognized even in a scientific paper that this is the number of days per year that the South Pole Station reported a minimum temperature below minus 73.3. This was my year, 1992. I guess there were seven days that the temperature was below minus 100. But I only did the 300 Club once. Okay, now on to water vapor, clouds, and precipitation. First, water vapor. What's called precipitable water vapor is the amount of water vapor in the atmosphere that if you condensed it all and brought it down to the surface as rain, how thick would the layer be of rain that you would produce? And in the mid-latitudes and tropics, it's typically 10 to 50 millimeters. So like that. That's precipitable water. That's water vapor in the atmosphere that could precipitate if you took it all out of the atmosphere. On the Antarctic plateau, it's lower by about a factor of 100. It's very low. And that's why the astronomers like to go to Antarctica, because in the infrared region, water vapor absorbs infrared radiation. So they can see through to infrared astronomy. It's good to go to a place either that's very high. They also go to the Atacama Desert in Chile, way up at 5,000 meters to get above most of the water vapor, or to Antarctica. Cloud cover, as I said, over the Antarctic Ocean in summer, it's the cloudiest region on Earth, about 90% cloud cover. Over East Antarctica, it's lower, but it's still 40%, but they're thin clouds. They're thin ice clouds, cirrus clouds, mostly. And here's some pictures of clouds. They're all summertime pictures because I took them in the sunlight. This is Cirrus Cloud. What surprised me at first, although I'd read about it, is to see clouds of liquid water, stratocumulus, stratus, altostratus, and these clouds, this is very clean air, and water droplets, small water droplets, just in isolation, will not freeze. Like a bucket of water will freeze at 0 degrees Celsius because it's got surfaces of the bucket to nucleate on. If you have a particle in isolation, there's an energy barrier to overcome. It needs a nucleus, like a dust particle, to freeze on. And if there's no foreign particle to serve as a nucleus for freezing, you have to cool it down to about minus 37, and then it will freeze as pure water. So we often have temperatures in clouds of minus 30, minus 20, minus 30, and the clouds are liquid. That's in the summer. In the winter, they're mostly just ice because it's too cold. It's below minus 37, even at the cloud level. Now, a common situation when you have a clear sky is that it's not totally clear. You look up and you see blue sky, but you look horizontally and you notice that you're actually in a cloud, in a thin cloud that's right at the surface. and it's a cloud of ice crystals. So you could say that you're in a cirrus cloud at the surface. It's called diamond dust because it's just small crystals that sparkle in the sunlight or the moonlight, and they're very tiny crystals, and they're ice, and well, actually the way it forms is with mixing. It's under a temperature inversion where you have warm, humid air above and cold air below, and any mixing will bring that warm air down into colder region where it'll be where the humidity will then become greater than 100% because it's gotten colder, and your crystals will form. And the kind of crystals you get are these very simple shapes, columns and plates, and they're ideal for forming halos. You get the most beautiful, most complex halo patterns from the simplest crystal shapes. Now, halos, most of you probably don't see them as often as you could. Every time you go out and you see a hazy sky that's not completely clear, put your hand in front of the sun and wear sunglasses and look around, and you'll very often see the 22-degree halo. That's this one, 22 degrees away from the sun. This is a wide-angle lens, so it doesn't look like it's 22 degrees, but 22 degrees. These other halos are much rarer, and some of them are hardly ever seen outside of Antarctica. Okay, and then snow accumulation. Well, this is a contour plot, and you see the minimum here is 5. This is centimeters of liquid equivalent. So, and as I said, at Bostock, it's only about 2 or 3 centimeters when you compress it into ice. That's the minimum. And then as you go out toward the coast, it's higher. And in the peninsula, it's greater than 40. So I say East Antarctic Ridge, 2 to 3 in centimeters, liquid equivalent per year. Average for Antarctica is about 17. And that compares with the global average, which is 100 or 40 inches. And that's about what Seattle gets. I suppose it's similar here, like the global average. So yes, Antarctica gets a lot less precipitation than the global average. But there is snow falling everywhere, and a lot less in the interior than around the coast. At the South Pole, 7 centimeters a year. A large fraction of the snowfall comes from a few warm storms. On the East Antarctic Ridge, where they get only 2 centimeters a year, it may be that most of it actually comes from diamond dust. This just slow, steady accumulation throughout the year of small crystals. During the last ice age, temperatures were lower and there was less snowfall. You know, if you've got lower temperature, then you bring in less water vapor from the ocean. So with future global warming, we expect more snowfall. We expect the air will contain more water vapor and you'll get more precipitation. And that is that's a way that Antarctica could contribute to lowering sea level, or at least counteracting other causes that increase sea level. In fact, Antarctica is now probably contributing to raising sea level because of this effect is being counteracted by the flow of glaciers into the ocean. The wind, the wind at the surface mostly is flowing downslope, away from the high regions out toward the coast, and it gets turned to the left as it flows down toward the coast. And that's because of the Earth's rotation. It's called the Coriolis Effect. The average wind speed at the South Pole is much stronger in the winter than in the summer. These are in knots. If you prefer meters per second, you divide by 2. If you prefer kilometers per hour, you multiply by 2. The meteorologists report in knots, which is like miles per hour. And I circled Cape Denison. This was kind of an unfortunate choice for Mawson set up his camp for the first Australian Antarctic expedition in 1911. The day they landed there was a calm day, but that was misleading. They set up their camp and then they spent a year there, and they have the world's record for the mean annual wind speed of 38 knots. some of you may have seen Mawson's book called The Home of the Blizzard. Anyway, there's Cape Denison. The winds in the interior are not so strong. It's where it gets funneled between mountains going out toward the coast that you get really strong winds. Now, the threshold for drifting snow, as you increase the wind speed, eventually snow particles get lifted from the surface, and then as they fall, they impact other particles, and they keep kind of feeding on itself, and you get drifting snow and blowing snow. Or in other words, a blizzard. And this was our first winter blizzard at the South Pole in 1992. So it's a wintertime phenomenon because in the summer the winds are rarely strong enough, but in the winter they're often strong enough to get drifting snow. Yeah, this was my own log through the year, nothing in January, February, and then these are blowing snow events a lot through the winter, and then November, December again, nothing. And these are what the blowing snow particles look like. They're little rounded particles because they've been colliding with other particles and breaking off their corners or sublimating their corners. There's also some falling snow particles at the same time. What happens on the surface then, you build you build up dunes, like in the desert, Barkhan dunes, and then they become immobilized as the crystals sinter together, and then they further wind action, they get eroded. And the result of the erosion are called sastrugi. It's a Russian word. And these are like erosional features that line up with the wind direction. And in fact, they're used in areas where there's been no weather station. They're used to estimate the direction of the prevailing wind, just looking at the direction of the sastrugi. So I did have one opportunity to ride on a tractor train going from Dome C down to the coast at Dumont d'Urville. This is how the French expedition supplies their station. They have 3 round trips by tractor train from the coast up to the Dome C. And driving one of these tractors, the wind is always blowing, and it's blowing from the right to the left, and it's building big sastrugi. Something about climate changes. Mean annual temperature. South Pole, no significant change, maybe a slight decrease. Antarctic Peninsula on the west side, very strong warming. That's one of the, maybe the most rapid warming places on Earth, on the west side of the Antarctic Peninsula. Snow accumulation, no significant change since 1956 there's probably been some change, but not detectable yet. The big change has been, as I mentioned earlier, these ice shelves. Here's one on the east side of the peninsula that broke up, the Larsen A, the Larsen B, and then last year a large part of the Larsen C ice shelf. So here was the front of the ice shelf, 1998, 1999, 2000, and then 2002. It's all gone. And as a result, see, this ice shelf was in contact with these islands that sort of held it back, and that friction is gone now. And this ice shelf was holding back the flow of these glaciers, the Crane Glacier. And immediately after the ice shelf was gone, these glaciers sped up. They're not being held back anymore. So that is how Antarctica is contributing to sea level rise now. The ice shelf, of course, was already floating, so breaking up the ice shelf doesn't change sea level. But these glaciers flowing down from the mountains behind it, that ice comes into the ocean and causes sea level rise. And they've seen here the speed of these glaciers increasing after the ice shelf is gone. So that's happening several places around Antarctica where the ice shelves are breaking up. Okay, some summaries about Antarctica. Depth of the ice, average 2.2 kilometers, maximum 4.8, about 86% of the ice in East Antarctica. The average annual temperature from -60 on the East Antarctic Plateau to -3 on the peninsula. I told you about the record low at Bostock and the record high at South Pole. And the average accumulation for the continent, 14 to 19 grams per square centimeter per year, or in other words, centimeters of liquid. And on the plateau, 5 or less. And then back to these Arctic-Antarctic differences. We talked about sea ice earlier, but now the ice sheets, comparing Antarctica and Greenland, they're quite different. Antarctica loses its mass 99% by icebergs and only 1% by melting, whereas Greenland is about half and half, icebergs and melting. There's a lot of surface melting on the Greenland ice sheet. In the summer, most of Greenland is covered with melting snow in the summer. So Greenland is much more, the surface of Greenland is much more susceptible to global warming. In the South Pole, you warm it up by a few degrees, it's still well below freezing, but Greenland is already undergoing melting. So that's an important difference between the Arctic and Antarctic. Oh, another thing which I didn't talk about, Antarctic snow is clean. Arctic snow is contaminated enough with soot, black carbon pollution to affect the albedo by a couple of percent, well, depending where you are. And that's enough to affect the northern hemisphere climate. Now I have a question, but I want to first get you this. Here we are, yeah. Question about ozone. Yes. Well, polar stratospheric clouds are, as I said, are a catalyst for destruction of ozone. Normally they're too thin to see, but where they flow over the mountains, where the airflow is over the mountains near the coast, then they become thick enough to see, and then they're called nacreous clouds. Because of the particle sizes, they're these beautiful multicolored clouds, and they're involved. They're required for the ozone destruction, but I wouldn't say it's their fault. These beautiful clouds, they were there before the chlorine pollution that's really responsible for destroying the ozone. Okay, so any more questions?
This is Karen over here on your right. On your right, yes. Is that compared to the Aurora Borealis and up in the north?
Okay, I did not show any pictures of the aurora. That nacreous cloud is not aurora. That's a cloud. The aurora, and that cloud is at about 23 kilometers altitude in the stratosphere. The aurora is caused way up at 100 kilometers, way up in the, I guess, the magnetosphere, well above most of the atmosphere. And the aurora is caused by the solar wind charged particles coming in. They get focused down by the magnetic field, and when they collide with oxygen and nitrogen atoms, they can emit light. Now, and you don't see it in the summer because the sun's up all the time. You only see the aurora when it's dark. And it's called the Aurora Borealis in the north, or the Aurora Australis in the south. And there have been instruments recording at the appropriate locations relative to the magnetic field, and they see that they are simultaneous. When you get an aurora in the north, you get the same aurora at the south, because it's the solar wind coming in that then goes in both directions. In the winter, at South Pole, I did not try to take pictures of the aurora, but I just enjoyed it. It was just white streaks. In fact, sometimes if the moon was up, it was hard to tell whether it was really aurora. It could be a moonlit cloud until it suddenly jumps to the other side of the sky, and then you know it's an aurora. But there were some spectacular auroras that were multicolored. And then there's one I remember, I just put on my parka and just laid down on my back to watch it because it was almost vertical. I called it the Aurora of the Dancing Needles. It was, yeah. So yeah, that's part of the winter experience in Antarctica. And if you want to see the aurora, let's see, actually a favorite tourist location for the aurora is in Canada at Yellowknife. Yeah, the hotels are actually full of Japanese tourists who come there to see the aurora.
A very important question. When they move the South Pole marker every year due to the flow of the ice, do they also have to move the sign to yonder?
That sign to yonder, I don't know how long it was there. These signs come and go. Now there was once, I wish I'd gotten a picture of it, but there was once a sign that was like that, with a wooden plaque with a tapered at one end to be an arrow, and it said north. And now, what direction do you suppose it was pointing? You're getting close. It was pointing like this.
Pretty cool.
Because yeah, that's the direction to the North Pole.
Oh, here's a question. What did it feel like to you to go from 200 degrees Fahrenheit to minus 100 degrees Fahrenheit?
Well, I didn't know what to expect, but afterwards I had a sore throat for a few hours. So I should have probably, put something over my mouth, because I was running, you're breathing hard. And so cold air was irritating my throat. And you kind of don't know until you do it, but that was the only ill effect.
This is Ken. How much trouble was maintaining the equipment in that kind of a climate?
Well, we were pretty well prepared for it. There's some things that you had to be careful about. Static electricity is a big concern, and so I had to go out the tower, and I had to press buttons on a data logger. I was measuring the angular reflection of sunlight, and so I had to turn some things around and then press a button. Well, there were two ways to avoid shorting out the electronics with a spark. One was I used a wooden rod to hit the button, and the other was that I had around my wrist a Velcro strap with a metal button attached to a wire attached to a clamp, and that all came out of my mitten. And so when I went up there, the first thing I did was I took that clamp and I clamped it to the metal part of the tower, and immediately I felt a shock on my wrist. So I had discharged static electricity. So that's kind of became routine to just do that. Just as a favor to Professor Otake from University of Alaska, I did an experiment for him, and he gave me this thing. Well, anyway, it required running a little air pump, and sucking air through a filter. But the wire for the powering of this, it had to run across the roof and into a socket, but he didn't have a cold, you can get proper wire that will remain flexible, where the insulation will remain flexible at very low temperatures, but his didn't. And so, I would try to carry it, but it was completely stiff. And then just under its own weight, it would break. So I had to rewire that thing. So it required, with my students, we spent a summer to try out everything, and then we came back and did repairs, and then went for the winter. And it was, of course, much colder in the winter than in the summer. I'd probably think of more things if I had some time, but those are the things that first come to mind. But I should say that there are some things that you don't have problems with in the Antarctic winter. There's no problem of rusting because there's no liquid water.
Hi, this is Anne. How much has changed since you were there in terms of the equipment or the comforts of your housing?
Well, now they have, I think they have windows in the bedrooms. Yeah. They have internet access. Now, when I was there in 1992, that was actually my introduction to email. I hadn't used email before, and it was, you know, it was there at the university, but I hadn't started using it yet. That was important, the fact that we did have email. 1992, it was, because I had 3 students who had given me their experiments to run during the winter, and each of them had a reason not to stay for the winter. So I had to have communications with them. You know, I was, 46 years old, and I had lots of responsibilities at the university, and so having the email was really essential. Actually, I should point out that for my personal life, it was a good year to be there because I was unattached at the time. I was between marriages, 1992. Now what they have now is not just email, but and the email we had back then, it would just you'd send it by email to the radio operator, and the radio operator once a day would send out all the emails for everybody on the station. The way it worked was we had NASA had a satellite, a geostationary satellite, supposed to just be above the equator. Now the equator, because if you're right at the pole, the equator is on the horizon, or actually, just below the horizon. And so the satellite was not in view from the South Pole if it's right over the equator. But it had lost its fuel, and so it was wandering in its orbit, and NASA had abandoned it and was allowing us to use it. And it went north and south of the equator about 9 degrees. So for a few hours a day, it was far enough south that we could see it from the South Pole. So during that time, the radio operator would send out all our email to this satellite over the equator, and then it would go down, be beamed down to a ground station in Miami at the University of Miami, the Atmospheric Science Center there, and then it would go out to wherever in the world. 1992, there was, in August 1992, there was a hurricane, Hurricane Andrew, that actually came right over Miami and did a lot of damage, including to the university, and our ground station there was shut down for a week. So people back in Seattle were wondering how come that they were not getting my email for about a week from the South Pole. It didn't occur to them it was because of a hurricane in Miami. But now they not only have email, but they also have internet access. So you can go onto the web, and that's a big difference in the way people live at the South Pole. I haven't been there since since the year 2001. So I can't talk about the more recent changes. Yeah.
Hi there. I think you mentioned that you were doing, you were doing core drilling, and you had these great big huge drilling things to do ice cores, and they went down, I don't remember what you said, 300 million years or something like that.
300,000.
300,000 years. So that's good. So in that 300,000 years, I've read that you can determine the amount of carbon dioxide that's been in the atmosphere over that period of time by looking at the ice cores. Is that true? And did you do anything with that?
Yeah. Now, I haven't done ice coring myself, but I do know about it because I've been, teaching in classes, and I've also gone and seen these ice core drilling operations. Bostock, I think they got down to 300,000. The oldest ice is 800,000 years, and that's at the French station at Dome C. So they have the longest record, 800,000 years, and they go through 8 ice age cycles. There's a cycle of about 100,000 years. The last ice age peaked at 20,000 years ago, and then we came out of it by 10,000 years ago. And yeah, and the carbon dioxide, actually this was discovered also at Dome C in a 30,000 year record back about 40 years ago, where they measured carbon dioxide in the bubbles in the ice, showing that there was less carbon dioxide in the atmosphere during the ice age. And now that they have an 800,000 year record, you can see it's really pretty repeatable, that every time during an ice age, the carbon dioxide goes down in the atmosphere, goes down to 200 parts per million, and then it comes up in the interglacial, like we're in now, to 280 parts per million, and then goes, between 200 and 280. And then it was steady at 280 until around the year, 200 years ago, and then it started rising because of human burning of fossil fuels, and now it's up to 400. Now, an important linking the ice core record, because the modern record is all from day-to-day measurements at several places on the Earth, but most prominently on the Mauna Loa on the island of Hawaii, up at 11,000 feet elevation. There's a station there, was established in 1958, and they're measuring continuously carbon dioxide in the atmosphere, and that's where they've seen it rise, starting at about 315 and going up to 400. So now, how did it get between 280 and 315? What was the sequence? How do we know that it was in the year 1800 it was there? Now the problem is that when the snow gets compressed into ice, and then at some depth, about 50 meters, the bubbles get closed off. Well, at Bostock or at Dome C, the accumulation rate of snow is so slow that it takes about 3,000 years before the bubbles close off. And all that time, the air is mixing between the surface and the snow. So you're getting a smeared out record, a smearing of 3,000 years. You don't have, a resolution to, to see short time scale variations. So for that, what you need to do is go to a place where the snow accumulation rate is much higher. And the Australians have done this. There's a small ice cap near the coast of Antarctica. It's called Law Dome, named after Philip Law, who was the leader of the Australian Antarctic program. And on Law Dome, instead of that much snow in a year, they get a meter of liquid equivalent. So it's like the global average. So very rapidly, in in a few years, the bubbles get closed off. So they record much more rapid variations. And from that ice core at Law Dome, they've been able to make the connection. From the ice core, they measure the carbon dioxide on up through the I don't know where they start, but maybe 1,000 years ago, up until 1958, and they overlap with the record from Mauna Loa and agree with it, so they get the continuous record now.
I'm afraid we've run out of time here, so thank you so much for a fascinating presentation.